this class. So yesterday we have talked about combinatorial optimization algorithms, and we have introduced one quantum algorithm to solve these problems, which was quantum annealing. And today we're going to see another quantum algorithm, which is the so-called QAOA, for quantum approximate optimization algorithm. So this was introduced by Edward Fari in 2014. And Goldstone. So the original reference, interestingly, it was not published, so it's on archive only, but it has become a seminal paper. And then I believe that with Laura, you are going to see the connection between the two algorithms. So there can be a sort of mapping between QAOA and quantum annealing in some sense. But today I will only focus on QAOA. And so we have seen, we've mentioned yesterday combinatorial optimization problems. And we have said that one of these was the so-called satisfiability problem, and this was NP complete. It means that if you can solve satisfiability, you can solve all the problems in NP with a polynomial overhead. So in particular, it means that we can, if we want, to formulate NP problems in that way. So then we are going to do it now and consider, like, in particular, an objective function that is given as the sum of different clauses that depend on binary variable. So Z is a collective string. Is what I called the X yesterday, Z1, Zn, where each Zi can be either 0 or 1. And so these clauses are Boolean expressions, typically, and we aim at maximizing this, so at satisfying the largest possible number of clauses. So in other words, C alpha Z is going to be equal to 1 if Z satisfies C alpha, or is going to be equal to 0 if Z does not satisfy. Then we can distinguish three cases. The first case is the case of really satisfiability, the satisfiability problem, where we ask if it exists Z that satisfies all the possible clauses. And we have M of them. So does it exist Z for which, let's call it a Z star, for which C Z star is equal to M. You see that if all the clauses are satisfied, the cost function sum up to M because there are M clauses. So then this is a decision problem and is what is called the SAT. Then we have the max SAT, which is the problem where we want to find the Z star that maximizes the cost function, not without necessarily saturating M. So the problem is find Z star maximizing C of Z. And the third version is approximate optimization. Where here we want to find the z for which the CZ is closer to the maximum. Find Z. And so QAOA and aims at solving this third point. So we aim at finding an approximate maximum, basically. So then how this algorithm works, I will really follow the paper by Fari, and this is why also in the notes, there are basically no notes for this lecture. I copy-pasted the full paper in the PDF that will appear online today, hopefully. So, so basically we define operators that are evolution operators that depend on two things. They depend in principle on the cost function and on the real numbers that are angles. So, and then they are written like this. With gamma in, I can also write it here. So gamma is in principle in 0 to pi. So basically this is an evolution operator under the cost function. So if you interpret this as a quantized Hamiltonian, we are going to do it later with specific example. This is a Hamiltonian that is diagonal in sigma z, say. Then we have another operator that is called U B beta, which is e to the beta b. And then with b, we can define it as the sum for j equal to 1 to n of sigma jx this time. So it's the orthogonal direction. This is going to be diagonal in z, and this is diagonal in x. And then here, if we substitute this makes the product for alpha, for j from 1 to n to the beta sigma jx. Okay, these are the two main operators of the algorithm. And here, beta can be chosen in 0 pi.
Excuse me?
Yeah.
C alpha is diagonal in Z because we defined it like that? Or?
Yeah, it's because it depends on binary variables. Is really what we have seen. So you can think about this exactly as the Ising Hamiltonian that we saw yesterday. You could really convert this into Ising Hamiltonian, and then you remember that the Ising Hamiltonian is expressed with the sigma z operators only.
Okay.
And one other way of seeing it is that it depends on the configurations, and the configurations are all configurations in the computational basis. So in your basis state z equal to z1 zn, you have a natural correspondence between the configurations of this register and the values of the binary variables that give a value to the cost function.
Okay.
It's quite natural. So in this sense, this is also why this is similar to quantum annealing in some sense. You are going to see, we are going to start from the same state that we were starting yesterday from. And then the goal is, which is diagonal. Let's write it down. What is the starting state? So the starting state is again the same for the quantum annealing. So is the eigenstate of sigma x for all the qubits. So then is the same eigenstate, so basically it's an eigenstate of Hamiltonian that are diagonal in sigma x. And then we start from this, and the goal is the same as quantum annealing, to arrive to prepare a ground state somehow of a Hamiltonian that is diagonal in Z, and that encodes the solution of the problem, which is this one. But with quantum annealing, you do this by staying all the time in the ground state and changing slowly the Hamiltonian. Instead, in this case, we are going to switch, we start from this, but then we don't stay necessarily in the ground state. We are going to apply a sequential sequence of these two algorithms in an alternating way. And then this it somehow prepares or tries to prepare an approximate version of the ground state of the final Hamiltonian. And then, yeah, there is a correspondence between the two. So you can understand the QAOA in the infinite limit of iteration as a trotterization of quantum annealing. But this Laura is really going to derive this result. And in the Fari paper, they mention this, even if at a heuristic level. So then, so the angles, they are like gamma 1. So now we are going basically to iterate a sequence of, as I was saying, we start from here and we iterate a sequence of these two operators, and we can alternate it p times. So that in practice, this algorithm depends on an integer parameter p, which is the iteration level of the algorithm. So then we can define the state gamma beta, like having applied UB beta p, UC gamma p, UB beta 1, UC gamma 1 over the state S. And then this gamma here, it's a collective index that regroups gamma 1 to gamma p, and the same for beta. So start from the ground state of sigma x, so something diagonal in sigma x, and then apply sequentially first the Hamiltonian depending on the cost function for a time gamma 1, then the mixing Hamiltonian for a time beta 1, and then repeat the sequence, and then you prepare a state. And in this state you measure. So now we are going to, one thing also that we can define before stating the algorithm, we are going to write really the sequence like in a computer science more or less flavor. Before doing this, let me define the cost function in the final state, like the expectation value of the quantized cost function there. And then what we have also is that we can define the maximum over the angle of this. And then what is heuristically one can show is that the limit for p that tends to infinite of this maximized quantity is equal to the max over z of the cost function. So this means that I didn't prove it. They more or less give arguments for this, and they also give evidence. And one can also more or less understand that if you repeat an infinite amount of times this procedure, then the expectation value of the energy on your prepared quantum state is what maximizes the cost function. So is if you put a minus sign in front, is the ground state of the cost function Hamiltonian. Okay, so now, so then how should one proceed? How does the algorithm work in practice if we want to do it like this? So what they state in the paper, I'm going more or less to copy what they say. So you can see it in two versions. So first, you basically set, so choose gamma and beta that somehow maximize f, the expectation value for a certain p. Then use your quantum computer to prepare the state gamma beta. Then you measure in the computational basis. So this is the same thing as saying that we get a string zeta from z, from which we evaluate the cost function. And then, so this we can repeat the same thing, now the same thing with the same sequence with the same angle, a certain amount of time. Okay, I don't know which letter should I use, L times. And then, so what they say is that enough repetitions produce a string of z that gives cz near or greater of the expectation value. So then this means that basically you are kind of happy because you found a configuration that gives at least a value of the cost function that is at least the expectation value or higher. And then this is supposed to be an approximate solution to the problem. So one thing that they say is that the crucial question is how to choose these angles. Because there are angles for which this is not at all close to the maximum. So one statement that they say is that one can, so if p doesn't depend on the number of qubits, then it is possible, so which is also heuristically, it depends on the problems, but then it is possible to choose gamma and beta from a grid, which number of points also does not depend on the number of qubits, and then you can search for the optimal angle efficiently, basically. So, so if p constant, then you can set a grid. Okay, this is not taken. So what they say is that they can more or less estimate that the partial derivatives of this function are bounded by something that is of order of m square is the number of closest square plus mn. So then this is efficient in the number of qubits, basically.
What is m?
M is the number of closes,
Oh, okay. Oh, yeah.
and n is the number of qubits. So then, so if what they state is that in the case that p does not depend on n, then the derivatives, yeah, basically. Let me put the index here. That means derivative, and we have m, we have n, we have p, we have. it can be g we are going to have later, it can be f. So the partial derivatives of this, or f prime simply. So the partial derivatives of this expectation value of the cost function, they are bounded. It means that it means intuitively that the number of points, so if you look for the angles, and if you take a grid that is find one of the inverse of this, then you don't miss up a minimum, the minimum or the maximum. It means that you are efficiently able to find the maximum of the cost function if you take a grid that then is of this or inverse order spacing. So then this is efficient in the number of qubits, the search. And then if you do this, then you can basically embed your steps, this to this, into a classical optimization routine, where basically you do this. You start with this, then you use this quantum computer to prepare the state. Then you measure in the computational basis, you get the string, and so on. And then when you are here, you repeat it L times. You evaluate, instead of evaluating CZ, you evaluate the cost function. So then this requires having done L measurements, because you need to have the average. And then from the average, basically, you do a classical optimization, where you look for the angles that are optimizing this value by using a fine grid, basically. That's the brute force thing. But the brute force thing is efficient if P is constant, if P doesn't depend on N. And then you do this many times until your classical optimization for finding the optimal angles converges. You can also note that if there is a further stopping criterion, that if in any of these steps you accidentally find a Z string that gives the minimum value, because you can be lucky eventually. So there is a non-zero probability. It's not the main focus of the algorithm, but there is a non-zero probability that you hit the solution by doing this procedure, then you stop. It's another stopping criterion, basically. But one for which there are not guarantees, I mean, with the solution.
So first you classically choose gamma and beta, right?
Yes.
And then, so where do you have to use a quantum computer here?
Here,
I mean,
to prepare the quantum state, because this is a quantum state.
but you can do that classically.
No, it's a quantum state.
You can calculate what the state will be.
Not efficiently.
Uh,
Like if you have a 100 qubit system and I give you gamma and beta, you can calculate the final state. That's right.
But maybe even if you would be able to calculate it, the question is what you want to find is what is the Z that minimizes or maximizes here the cost function. So you need I mean, from even if you would be able to calculate even the expectation value.
So gamma beta is the set, right? Is it not?
Hmm?
Gamma beta, the state gamma beta will be the Z after a while?
So yeah, that's a good question. That's a very good question. No, but what happens is that from here, when you have calculated it, what you do is you measure Z. What it means, so the probability of hitting a string Z is the overlap square of this state in the final state.
By Z here you mean the solution?
Z is a string, it's whatever string. So this will be a superposition, you know, it will be
okay.
A superposition of like many possible strings, including with a certain probability, there will be also a C star, Z star, with a certain probability. This is most probably inside here, because we start, by the way, we started from a configuration that is a superposition of all the possible configurations. So the initial point also has the
Z star.
the Z star. It's just that the distribution, if you plot, for instance, the probability as a function of the cost function, the starting distribution is flat. Or then it depends on the, I mean, it's flat in Z, but it will not be flat in the cost function because it depends on the cost. So for some problems, it can be something like this, where you have a tail on the solution would be okay, here I'm thinking about minimization because I'm used to that, but say if you are minimizing, the solution would be this point here. Then after one run of QUA, your distribution changes and it becomes something like this, where you have more spikes here. And after more runs of the QUA, your probability of hitting the configuration with the good cost is exploding. This is a way of seeing that it works. And yes, in the beginning, you have, in terms of Z, it's really flat in the beginning. And then with different iteration, you get different distributions. And with enough iteration, you have a high probability of the Z star, that is your solution. It's very heuristic.
But again, why is it said that you can't calculate the diffusion? It's I mean, what will be the size of matrices if you have 100 qubits? So the U's and all are just single qubit operators, right?
Mm-hmm.
No,
Only this one.
you see, so the C can have sigma C terms, so you will get entanglement from all of them.
Okay.
Yeah, no,
So the Ising Hamiltonian can have CZ terms.
Okay.
We are going to write examples of the cost function, and yes, it will have sigma z, that you then concatenate every time that you use the UC gamma 1, or gamma 2, or gamma p. Yeah, so it's not easy to gain understanding of what this means, but also one thing that it does is that it maps the problem. Basically this does the QAOA. It maps the problem of finding the minimum or maximum of a cost function in the space of the configurations Z that are exponentially large, because the space here is 2 to the n, into the problem. It maps this to a landscape of the cost function in terms of angles, and these angles are not an exponential number, but they are proportional to p. So they are 2p, basically. Every time there are 2p parameters. So if p does not depend on n, it's a big gain in the number of parameters on which you have to look for the minimum. And then what they show is that, or like what one can heuristically be convinced of, is that when you find the minimum of or the maximum of the energy in these angles, then your probability of hitting the solution state when you do a measurement is high. There is some kind of performance guarantee, but for the specific example, we are going to do a specific example now. So there is a performance guarantee that one can put that are a bit more explicit.
And what decides P?
Yeah, that nobody knows.
Okay.
Nobody knows. That's the problem. It is heuristic.
Yeah, I mean, we have to decide P to get a certain quality of the approximation, right?
Yeah.
So, yeah.
We decide, but it's no guarantee that you can go, how many, what approximation ratio you will get with a P of your choice. There is no guarantee that to get a good one, you must not have a P depending on n. But they show that for some example, they can have with a fixed P equal to 2, some approximation ratio that are higher than what is known with best classical algorithm, for instance. That is also not written in stone because people can always come up with a better classical algorithm. But at least it's a heuristic understanding that it works.
So right now we just randomly choose P, or is it based on any criterion?
Not randomly. Experimentally, you want it as small as you can, because to each P it translates a depth of the circuit that you have to build. And with nowadays coherence time, Andreas, they did an experiment in the lab at Chalmers, and they were bounded to P equal to 2, because already for P equal to 3, they had too much noise in the fidelity of the gates were like spoiling the ability of preparing the state with a good fidelity.
So I mean, it sort of depends. Like you would start with P equal to 1 and see, you know, how often do I hit the state that I want.
Okay.
And if that's not high enough, okay, you try to add, then you go to P equal to 2, for example.
So you do it for problems that you already know the solutions to?
Yes, currently, yeah. Because I mean, our processors are so small, so we can solve them
Okay.
on like a classical computer and check the answers.
Okay.
And also there are results that show that if P is square root of n, then the algorithm is universal. It can prepare any state, so it becomes a universal quantum computer. So it means that, but then the search in particular of the angles is not necessarily efficient anymore. So then you don't want that. It would be very nice if people are trying to prove results that even with log n, P equal to log n, it would be universal, but there is not a result available at the moment. It's a research area. Okay, I will now erase and we start with the example. The example will take some time. So we start and we can then maybe stop in more or less in the middle. I wonder what I should erase because we want to use all of this. So it's a bit bad that we want to use all of this basically. But I don't have a second word, no. So we have to live with that. Will you remember? I can give you, yeah, I can also give you the paper to, okay. So then we start with then fix the P for the reasons that we said, and we want to. So I make the example that they do, where they focus on WACQT as a problem, which is in particular. So it's also expressed like before. We have a cost function that it depends on a graph. So you take graphs with bounded degrees, which means that the number of the edges, so the connections for each vertex does not depend on n. So and then so we have a graph with n vertices and edge set jk of size m bounded, so it's constant. And then so this cost function can be written like this. And what we want to do, the problem is to find basically is a little bit, you can think about it like coloring the edges, the vertices into colors, where like either black or white, where you want that the largest possible number of vertices that are connected by an edge are colored in different colors. If they are, you can cut the edge somehow. So it's like assigning the edge, the vertices of the graph to two subparts, right or left, or two colors, such that you maximize the number of cuts, and you have a cut if you color the two vertices in a different color. I don't know if I can make an example. So, okay, we will later give, let me spoil the example that we will see later, where we will calculate everything also, where the graph is this one. It's a ring. So that's a very simple example here, clearly, intuitively, the number, so basically you want them to disagree. You want that the different vertices disagree, the largest possible number of disagreement in the graph.
Okay.
And you can see that it translates by this, because agreement will be that this have the same sign, and then this will be plus, then minus, it will be 0, and largest possible disagreement maximizes this cost function, because then these have different sign, and this becomes positive. That's why this is the cost function for the max cut. So then, in particular, so then let's write explicitly the expectation value that we have. Is now what we want to maximize is this expectation value, which is, I use the formulas. Actually, it's quite good because we can now rewrite everything. I write and then I say what we are doing. JK, let me call them JK. Did I call them JK? Yes. No, JK. And okay, JK even here. Okay, so basically what is this? Is what we said before. So we start from the starting state, which is the superposition of all the states. Then we apply the first Hamiltonian depending on the cost function, then the first mixing Hamiltonian. Then we go until P, and then we want to calculate the expectation value of the cost function, because this was the definition of F at a level P of iteration. Then written explicitly, it reads like this. Because we have just, what we did here is writing explicitly the cost function, so the expectation value of the cost function in the finally prepared state for optimal angle gamma and beta. Okay, so now we want to notice that we can, due to the structure of this problem, we can basically do the optimization over the angles aside from the quantum computation. We don't need the embedding. And we are going to demonstrate this. So the key point is that the operator, so this operator here, let's write what it is. You will see that it only involves qubits that are either on the edge JK or at most P levels away from it. Is the most that we can manage to entangle with a P iteration and the definition of the operators that we have. So basically what happens is that this, let me write it here, this So only involves qubits j, k, and those at distance, maximum distance p from j and k. So basically the number of qubits that enter here is bounded. Then we have to sum on each j and k. But this allows to simplify things quite a lot. So for instance, if you take the case p equal to 1, then this operator becomes sigma j square x and sigma k x, and then minus beta sigma j x sigma k x u sigma 1. So basically here, if you remember from the definition, when you apply, so we are looking at this term now for p equal to 1. So I only have to take the terms p equal to 1. And if you remember from the definition of the operator b, it's the product of sigma x over all the qubits. But since here there are only qubit j and k appearing due to the definition of the cost function that are only j and k, then all the other terms in the product that are not j or k, they annihilate each other because they commute with this, and then it's the product of the unitary with the conjugate. So they all go away. So the only terms that resist are these. And then in the cost function,
Excuse me,
yeah,
but p is already 1, right? So there is only one beta 1 term. There
yeah,
are no-
here there is only a beta 1, yes. But no, but you are confusing the number of qubits with the number of angles. If you remember, the definition of B is the product of all the sigma xi over the qubits. So it means that in principle here there should
Okay,
be
okay.
on all the qubits.
Okay.
But the others commute, so they go away. And then if you now look at the Hamiltonian, how it works, it can only connect terms, so this it means an edge. So it can only connect the terms that are one extra away from j or k, basically. Because I only have this kind of nearest neighbors term that depends on the edge in the cost function, in this specific case. Then, yeah, it means that there are only a limited number of subgraphs that contribute to the cost function, and then we will have to sum over the subgraphs. But let's first evaluate what it is. So then, yes, the conclusion of this is saying that each term in this sum, let's call it equation, I don't know, FP. So each term jk in FP only depends on qubit jk and those away max p. So then it means that we can rewrite it yet again in a simpler way. But then let's focus on a specific example of 3 regular graphs. So the degree of a graph, by the way, is the number of edges incident on a vertex. So here we have a maximum 3. So then in this case there are only possible 3 subgraphs that have for edge jk, and these are the following. So this is the edge jk, and then there is this subgraph, or this is my edge jk. The other possibility with maximum 3 edges is this one. And the last possibility is this one. Then it's a bit formal. I don't know how much in the detail of I should go, or if I should give the result. Maybe I should give the result. So basically, you can, is to convince you that you can write this in the following way. We can skip maybe the formalities, it's quite intuitive. So then this will be the contribution of the cost function, so these terms on a specific subgraph. Associated to subgraph G, where G can be either this or this or this, and then I have to put a weight on the number of subgraphs that are in my graph, and then some on G. But the point is that, so then this becomes, it's independent on N and M, so it can be evaluated efficiently. And how many subgraphs there are in a graph of size n is at maximum linear in n. So eventually this can be computed efficiently in this case. It means that one can minimize for gamma and beta and find the optimal angles. It doesn't mean that it can be computed efficiently in terms of the configurations, but what I was saying before is that we have converted the problem of finding the minimum configuration in the problem of finding the minimum angles. I mean the optimal angles, maximizing the cost function. So and this here in this case can be done efficiently. And then when you find these optimal angles, you can produce your quantum state and measure Z and extract your strings Z, and with a high probability you can have the solution. And actually in this case it is possible to bound. There is a performance guarantee, and then I will stop after this for the break. The second part will be a bit shorter anyway. So here there is, so if we want to restyle the algorithm in this case, so you find gamma and beta maximizing FT classically, then produce with the quantum computer the state, measure Z, so measure in the computational basis, get Z, get C of Z, and then here there are performance guarantees. So repeating gives samples of C of Z between 0 and M with mean FT, And then this is the performance guarantee that an outcome of at least Fp gamma beta minus 1 is obtained with probability at least 1 minus 1 over m. I don't remember if you measure n times. It's probably if you measure n times. M log m. Okay. So this is a performance guarantee that they can evaluate. It means that if we measure a certain amount of times, you are guaranteed with a very high probability, that a probability that is bounded to be high, that you get a good outcome that is quite like where you kind of are not too far away from the expectation value. And then also they show that the probability distribution concentrate. I mean, this is so it's related to this. Is that so the spread of the probability distribution is basically proportional to square root of m. So in this case, they can kind of evaluate the performances in this sense. Other questions? Otherwise, we should stop for the break. But questions before? Okay, then we stop here, and then there is a further example, hopefully clarifying things after the break.